Hello, everyone. In this section, we will discuss voltage regulation as an application of diodes in electronics. The purpose of a voltage regulator is to provide a stable DC output voltage. Ideally, this output voltage should remain as constant as possible. When a load is connected, output current flows and may slightly change the output voltage, so we want this change to be as small as possible. Also, the original DC power supply itself may fluctuate. In that case, the voltage regulator should reduce the effect of those supply variations on the output voltage. How can we design a voltage regulator? One method is to use a forward bias diode. When the diode conducts, its voltage drop is relatively stable, which is the idea behind the constant voltage drop model. Let us first review the characteristics of a junction diode. In DC analysis, if the diode is forward biased and conducting, we can use the constant voltage drop model. The diode voltage is approximately 0.7 volts, and its DC resistance is treated as zero. However, when a small AC signal is applied on top of the forward bias operating point, the diode appears as an equivalent small signal resistance, RD, to the AC signal. Next, we introduce a voltage regulator made by connecting a resistor and several diodes in series, as shown on the left. The power supply provides a 10-volt DC output, but it also has plus or minus 1 volt of ripple or instability. The 10 volts is the DC bias source, while the plus or minus 1 volt variation can be treated as an AC voltage variation. The output voltage, VO, is the total voltage across the 3 series connected diodes. First, we perform the DC analysis using the constant voltage drop model. Each forward bias diode has a voltage drop of about 0.7 volts. Therefore, the output voltage is approximately 0.7 plus 0.7 plus 0.7, which is 2.1 volts. The diode conduction current is the same as the current through resistor R. It is 10 volts minus 2.1 volts, all divided by 1 kilo ohm, which gives 7.9 milliamps. Next, we move to the AC small signal analysis. Each diode can be modeled as an equivalent resistance, RD. Here, RD equals N times VT divided by the DC diode current ID. Substituting the numbers, RD equals 22 times 25 millivolts divided by 7.9 milliamps, which is about 6.3 ohms. In the AC equivalent circuit, resistor R is in series with the 3 diode small signal resistances. Therefore, the small signal output voltage is determined by voltage division. The plus or minus 1 volt supply ripple is multiplied by the fraction 3RD over R plus 3RD. This gives about plus or minus 18.5 millivolts at the output. In other words, the plus or minus 1 volt fluctuation from the power supply is reduced to only plus or minus 18.5 millivolts at the diode output. Finally, the total output voltage is the DC output voltage plus the AC output variation. Therefore, VO is about 2.1 volts plus or minus 18.5 millivolts. The original power supply has plus or minus 1 volt of instability, but only plus or minus 18.5 millivolts appears at the output. That means only 1.85% of the supply fluctuation is transferred to the output. Compared with the 2.1 volt DC output, this 18.5 millivolt variation is only about 0.88%. This shows that the output voltage is quite stable, which is the effect of voltage regulation. Overall, even though the power supply itself has about plus or minus 10% variation, the regulated output changes by only about plus or minus 0.88%. Next, let us see what happens when a load resistance, RL, is connected to the output terminal of this voltage regulator. Again, we begin with DC analysis. After RL is connected to the output, current flows from the output terminal into the load. This load current is IRL equals 2.1 volts divided by 1 kilo ohm, which is 2.1 milliamps. The current entering the output node through resistor R is 10 volts minus 2.1 volts, all divided by 1 kilo ohm, which is 7.9 milliamps. Therefore, the current flowing through the diodes decreases to 7.9 milliamps minus 2.1 milliamps, which is 5.8 milliamps. Now we perform the AC small signal analysis. The diode resistance is RD equals N times VT divided by ID, which is 2 times 25 millivolts divided by 5.8 milliamps, or about 8.62 ohms. At the output node, the three diode resistances in series are in parallel with the load resistance RL. This parallel combination is then in series with resistor R, so the output ripple is found by voltage division. In the formula, the numerator is the parallel combination of 3RD and RL, and the denominator is R plus that same parallel combination. Since RL is 1 kilo ohm, which is much larger than 3RD, the parallel combination is approximately 3RD. Therefore, the output ripple becomes about plus or minus 25.2 millivolts. As a result, under the plus or minus 1 volt supply variation, the output variation of the loaded voltage regulator is only plus or minus 25.2 millivolts. This corresponds to 2.52% of the supply variation. Relative to the output voltage itself, the variation is about plus or minus 1.2%. Compared with the no-load case, where the variation was plus or minus 0.88%, the regulation becomes slightly worse after the load is connected. What should we do if we want a regulated output voltage with a higher voltage value? The most direct method is to increase the number of series-connected diodes. Since each forward-biased diode provides about 0.7 volts, 10 diodes in series would give an output voltage of about 7 volts. However, using more diodes increases circuit cost. So the question is, how can we obtain a higher output voltage with only a small number of diodes? This is where the Zener diode becomes useful. By operating a Zener diode in the reverse breakdown region, we can achieve this goal. Let us quickly review the Zener diode characteristics introduced earlier. As shown in the figure, when a Zener diode is forward biased, its behavior is similar to that of a general diode. Therefore, it can be treated like an ordinary diode under forward bias. Under reverse bias, however, a Zener diode can conduct when the reverse voltage is large enough to cause Zener breakdown. This reverse conduction behavior is exactly what we want to use. As discussed earlier, Zener breakdown occurs when the p-type and n-type doping concentrations are both high. This makes the space charge region very narrow, allowing carriers to conduct through quantum tunneling. Because this tunneling current does not come from structural damage in the device, the behavior is reversible and repeatable. This is different from avalanche breakdown, which is usually irreversible. Next, let us look at the equivalent circuit of a Zener diode under reverse operation. Before the reverse voltage reaches VZK, the diode is not conducting, and only a very small leakage current, IZK, exists. After the reverse voltage exceeds VZK, the conduction current increases almost linearly, as shown in the figure. The reverse conduction current voltage relationship of a Zener diode can be written as VZ equals VZ0 plus IZ times RZ. Here, IZ is the reverse conduction current when the diode operates at reverse voltage VZ. VZ0 is the x-axis intercept of the linear current voltage line as shown in the diagram. The slope of this line is 1 over RZ. From this reverse conduction equation, we can build the equivalent circuit of the Zener diode. It is modeled as a voltage source VZ0 in series with a resistance RZ. This equivalent circuit satisfies the equation VZ equals VZ0 plus IZ times RZ. In general, VZ0 can range from about 2 volts to more than 10 volts. Therefore, to obtain a higher regulated output voltage, we need far fewer Zener diodes than ordinary forward bias diodes. Now let us analyze a voltage regulator using a Zener diode. The circuit shown has a resistor R equal to 0.5 kilo ohms in series with a reverse-connected Zener diode, operating with a DC supply voltage VDC of 10 volts. The Zener diode specification is as follows. When the reverse voltage VZ is 6.8 volts, the reverse conduction current IZ is 5 milliamps, RZ is 20 ohms, and the leakage current before reverse turn-on, IZK, is 0.2 milliamps. First, we perform the steady-state DC analysis. Using the Zener reverse conduction equation, VZ equals VZ0 plus IZ times RZ, and using the given specification that VZ is 6.8 volts when IZ is 5 milliamps, we can solve for VZ0. The result is VZ0 equals 6.7 volts. Therefore, we obtain the equivalent circuit of the Zener diode in reverse conduction, as shown on the right. With the equivalent circuit, we can directly calculate the diode conduction current under VDC equals 10 volts. ID equals VDC minus VZ0 divided by R plus RZ. Substituting the values, this is 10 volts minus 6.7 volts divided by 0.5 kiloohms plus 0.02 kiloohms, which gives 6.35 milliamps. Then the output voltage VO equals VZ0 plus ID times RZ. This gives 6.7 plus 6.35 times 2, which is 6.83 volts. Therefore, the output voltage of this circuit is 6.83 volts. If the voltage source VDC has a plus or minus 1 volt variation, or in other words, a supply instability, we can analyze the variation using small signal or AC analysis. The AC equivalent circuit is shown on the far right. In AC analysis, the DC voltage source VZ0 is treated as a short circuit. This is because an ideal constant voltage source has no voltage change regardless of the current change. Therefore, its equivalent small signal impedance is delta VZ0 divided by delta ID, which equals 0 ohms. That is why it becomes a short circuit. Therefore, when the unstable VDC has a plus or minus 1 volt variation, the output voltage variation is delta VO equals delta VDC multiplied by RZ over R plus RZ. The fraction means RZ divided by the total series resistance, R plus RZ. Substituting the values gives plus or minus 1 volt times 0.02 over 0.5 plus 0.02, which equals plus or minus 38.5 millivolts. In other words, when the supply voltage changes by 1 volt, the output changes by only 38.5 millivolts. This ratio is called line regulation. It is delta VO divided by delta VDC, or plus or minus 38.5 millivolts per volt. This means the supply instability is reduced to only 0.0385 times at the output. If a load resistance RL is suddenly connected to the output, causing a load current IL to flow into RL, the output voltage will also change, as shown in the circuit diagram. Because the output voltage is VO equals VZ0 plus ID times RZ, any sudden load current IL will reduce the diode current ID. Therefore, the current flowing into the load becomes the change in diode current, delta ID. If IL is 1 milliamp, then delta ID is negative 1 milliamp, meaning the diode current decreases by 1 milliamp. As a result, the output voltage changes by delta VO equals delta ID times RZ, which is negative 1 milliamp times 20 ohms, or negative 20 millivolts. This effect caused by adding a load is called load regulation. It is defined as delta VO divided by delta IL, which equals negative 20 millivolts per milliamp. This means every 1 milliamp of output load current causes the output voltage to decrease by 20 millivolts. Let us look at the load case from another perspective. Suppose a load resistance RL equal to 2 kiloohms is connected to the output. From the previous DC analysis, before the load is connected, the regulated output voltage is 6.83 volts. We first assume that after the load is connected, the output voltage is still approximately 6.83 volts. Then the load current IL is 6.83 volts divided by 2 kiloohms, which is about 3.4 milliamps. Therefore, because the load current IL flows out of the output voltage changes by approximately negative 3.4 milliamps times 20 ohms, which is negative 68 millivolts. This is an approximate result. To obtain a more accurate result, we can use iteration. Based on the first approximate value of IL, we adjust the reduced diode current ID, then update the reduced output voltage VO. After that, we recalculate the new resistor current IR and load current IL. After 2 rounds of correction, the result settles, and the difference from the no-load output voltage is about negative 70 millivolts, which is very close to the previous approximation. What if the external load resistance RL is only 0.5 kiloohms? Using the previous approximation, the load current would be IL equals VO over RL, or 6.83 volts divided by 0.5 kiloohms, which is 13.66 milliamps. This current is much larger than the no-load DC current, IR or ID, which is 6.35 milliamps. This is impossible. Therefore, in this case, the Zener diode is not in reverse conduction. In other words, the diode is cut off. Therefore, the output voltage VO must be recalculated. Since the diode is open-circuited, as shown in the equivalent circuit, the output voltage is determined by the voltage divider formed by R and RL in series. Therefore, VO equals VDC multiplied by RL over R plus RL, which gives 5 volts. From the previous example, we can see that as RL becomes smaller, the load current becomes larger. This reduces the current flowing through the Zener diode and eventually forces the diode out of reverse conduction. Therefore, to keep the Zener diode operating in the reverse breakdown region, RL must be above a certain minimum value. Let us calculate that minimum value. When the diode operates right at the edge of the reverse breakdown region, the diode voltage VZ, which is also the output voltage VO, is approximately VZ0. At this edge condition, the Zener leakage current before reverse conduction is IZK, which is 0.2 milliamps. Therefore, we first calculate the current through resistor R under this condition. IR equals VDC minus VO divided by R. Substituting the values gives 10 volts minus 6.7 volts divided by 0.5 kilo ohms, which equals 6.6 milliamps. Among the current IR entering the output node, part of the current must remain in the Zener diode. This diode current is ID equals IZK, which is 0.2 milliamps. The remaining current can flow into the load RL. Therefore, the maximum load current is 6.4 milliamps. Finally, the minimum allowable load resistance is RL equals VO over IL. This is 6.7 volts divided by 6.4 milliamps, which is approximately 1.05 kilo ohms. However, if VDC itself has plus or minus 1 volt of instability, we can also calculate the minimum allowable RL when VDC is at its lowest value. In this case, the lowest supply voltage is 10 volts minus 1 volt, which is 9 volts. When VDC equals 9 volts, the current through resistor R is 9 volts minus 6.7 volts, divided by 0.5 kilo ohms, which equals 4.6 milliamps. Then the current flowing into load resistor RL is IR minus ID, which is 4.6 milliamps minus 0.2 milliamps, giving 4.4 milliamps. Finally, RL equals VO over IL, which is 6.7 volts divided by 4.4 milliamps, or 1.52 kilo ohms. This concludes our introduction to voltage regulation. Please look forward to the next lecture. See you next time. Bye-bye.